We have still some time. We'll go to the next part, but I don't know whether we can finish it. If not, we have about 20 minutes. Let's see. At least start the discussion. We might need to come back and finish it. So we'll go back to the Hankel function to evaluate the asymptotic expression. And this section, the textbook has two methods. One is this steepest descent method, or the saddle point method, which we use it in the gamma function to derive the Stirling formula. If you remember that, you can do exactly the same. And then there's a more complicated method, the second method, which give you more terms in the asymptotic expression. Actually, that's the exact form of all the terms, or the series, the asymptotic series. But we only go through the first part, because the second part is really long. The other reason is that we seldomly need more terms asymptotic series. At least I haven't used other terms. Mostly you just need the leading order would be enough. But if you really need it, if you have some application, you really need other term, you just look that up. So these are available in math handbook, right? And we don't necessarily need to go through that. It's okay. So we'll just go through the saddle point method, because again, this is an illustration of a general method that you can use for other integral. Right. So we'll do that, and there are two ways to apply this saddle point method. One is just look up the formula. I think it's chapter 12, a section in chapter 12, 12.7. You can look up the formula and just plug in the formula. That's one way to do it. Another is just go through the process and just like what we did for the gamma function, just transform your integral to some kind of a Gaussian integral, and then use evaluate the integral that way. Okay, so either way is fine. So it's not a whole lot of difference. So we start with this, what we talk about for the Hankel function. We use the one because the second one, if for real argument, is just the complex conjugate of the first one. And for some reason, the textbook interchanged the dependency variables. The original is defined as a function of c, as a function of t. T would be the integration variable. Now it's interchanged in this section. Likely it's because we will do a complex integral. So in that case, we usually use z as the variable in doing integration, which is fine. Okay, so that's how we define this H1. And remember this, the contour C sub 1. Now this is changed to the Z plane instead of a T plane in that the previous figure. But the branch point is still at the origin. So there's a branch point. And the C sub 1 is defined as you go out from 0, this is 0. And then go out along the positive. Now the positive real Z axis a little bit, and then you can turn. It's just for argument's sake, you can always go out anywhere you like because it's analytic. But for argument's sake, you go out the positive real axis and turn around. and go to negative infinity above the branch cut. The branch cut is cut to negative infinity. Okay, so that's C1. It's okay, so that the start from 0 goes to negative infinity, and the phase angle of Z is chosen to be 0 here. So this is pi. So this is minus infinity or infinity e to the I pi. Okay, so that's the contour C1. So now the asymptotic expression means we're taking Z goes to infinity, right? I think Z goes to infinity. So, and now compared with the form of the section in chapter 12.7, we are writing is the exponential function is called W, right? And there's a choice to do. You can include the rest of the integral. So this factor is Z to the nu plus 1 in the denominator power, and you can like write it as whatever function is the exponential of the log of this one. So whatever this power, and include that in the definition of W. I think we did that for the gamma function. That becomes there'll be a log part of this factor, and that would be more exact. Another way to do it is just treat the Z, this part evaluate at the center point, whatever the center point is. Finally, this part give you an integral, like a Gaussian integral. But the rest you just evaluate at the center point. And this is not so exact, and this can give you only the leading order, because obviously when you include that in the definition of W, the center point will change a little bit, but because the most the largest contribution is when I should say the t goes to infinity, not z goes. T goes to infinity. T is multiplied by the rest. When t goes to infinity, the exponential function is dominating the behavior. So the saddle point is very narrow. So over the saddle point, the rest is almost like a constant. So to leading order, you can treat the rest of the integram just evaluate at the saddle point. It's okay. So that's another choice. So for our purpose, it's okay. So we'll do that because we only want the leading order. The rest of the series, if you want, you need to sit. You can go to the second method in this section to get the rest of the series. Okay, so that's what we'll do. And now we change W. This part is W. And what we mean by saddle point is that this extremum, this W at the saddle point is an extremum, because it's an analytic function, and on the complex plane, it cannot be a global maximum or global minimum. An extremum, which means the derivative of W with respect to Z is 0, and that cannot be a global maximum or global minimum. It can only be a saddle point, which means it's maximum along certain direction and minimum along other direction. Okay, so that's what we do, and then first we just determine where are the saddle points. The W is given by this T, 2, C minus 1 over Z. To determine the saddle point, we like to take the derivative of with respect to Z. So this gives you T over 2, 1. And this gives you plus 1 by Z squared. And set it to 0. So this means Z squared equals to minus 1, right? The Z is equals to plus or minus I, right? So that would be 2 saddle points. So now you want to cause the saddle point, or cause the contour want to cause the saddle point, go through the saddle point, okay, and then we actually want to go through the value. So this is, I chooses the minus I, this I, and there's a corresponding saddle point is minus I. Okay, and now to determine where are the value and mountain around the saddle point. So the saddle point is basically whatever the saddle point, if you have a perspective plot, like if you have saddle point here over this, this is the value of the, say, value of W, this is like Z, this is the C plane, right? And so it's maximum along certain directions, so it may be maximum, right? And then a minimum over other direction. It's kind of hard. You just need to use some imagination. It's like a saddle, right? Saddle point is it's like that, the shape. And you want to cause the saddle point over the value. Basically, you want to go something along the value, right? You don't want to go up the mountain, because when you go up the mountain, then you take a lot of extra evaluation of this exponential function, become extremely large, although finally you get the same result because of cancellation, but you don't want to do cancellation. You want to go through a path that you just pick up the most important contribution and the rest will be small. You want to go along a path like that, okay? So you want to determine where will be the mountain and the value, which will depends on the phase. Right? We'll figure that out a little later, but assuming a certain mountain, and if the saddle point is like that, if you have a mountain over these two sides and value over these two sides, so you want to cause it over the value. And once you get past the rest, is okay, right? Because this is minimum with respect to this, you just always stay lower than this point. The contribution will be mostly from this point, right? Because it's but this path is the maximum, and go into the exponential function will amplify the maximum. So the most contribution is coming from this maximum. Okay, so that's what we'll do. How's time? 5 minutes. All right, and let's just do a little bit more and continue on next time. And what we do is just do the expansion of W about the saddle point. So we choose that. And another consideration, because there are two saddle points, you just pass through this upper one because you want to go to the infinity, negative infinity above the branch cut, which is the negative real Z axis. So if you go through this one, so if you go through this one, then you cannot go to here. You cannot go to here. So somewhere along the line, you will go back, right? So you basically cancel your own contribution. So there's no point going through this saddle point, right? So you only need one saddle point to go through what you want to get, right? So you can ignore this saddle point. So you choose your saddle point as I. Or in our case, we want to choose it more exactly because the phase here is 0 to pi, so this is I, e to the I pi over t. Right. So we choose this is our saddle point. Right. And now we want to do expansion of this W function about the saddle point. So W will be approximately W at the saddle point plus EW EC at the saddle point minus C sub 0. And up to the second order, E square, evaluate at the saddle point, D minus C 0 square. And you ignore all the higher order terms, right? And the first thing you do is by design this dWdz is 0, so you forget about this one. And W evaluate at C0, you can just do it here. So z at z0, this is I minus 1 over I, which is I plus I. So you have 2I, right? So 2I cancel 2. So this is just t I times t. This is I times t. And put it back to the exponential function. This is exponential I times t. Right? And this is the t is the argument of your Hankel function, right? So before you do anything else, now you know that the most important leading order asymptotic behavior of this h1 is exponential it. So before you can do anything, once you figure out the saddle point and evaluate the argument over the saddle point, you know that this is the most important contribution. And secondary contribution will be coming from this factor, because now we already mentioned that we will evaluate the rest of the integram at the saddle point. So basically chooses z, we could say I to the power nu plus 1, or exponential function, the exponential I pi over 2, the nu, and then the nu plus 1 power, right? And that will be a second contribution. That may not be the second leading order, because that's another contribution coming from the integration of over the Gaussian. And that we'll need to figure out a little later. And let's do one more step. Is this d squared, d double d squared. Because we already have this here, so we can just evaluate that. d squared wdc squared is now you have this is 0. This is minus 2 over CQ, so minus P over CQ. Right, and then now finally you evaluate that evaluate this at C sub 0, and that is this is I, right? Or you can use that exponential function. So it's minus e to the minus t. I should say t. T plus the exponential function. This is in the numerator, so it's minus 3I over 2I. Okay, so that's this part, right? And most important is the phase. This is the phase that will determine where we'll path where this orientation of this path. What is the basically we need to figure out the phase angle. If we pass this angle, we need to figure out this phase angle, whatever this theta is, or theta 0, whatever you call it. The theta of the relative to the saddle point, what angle we want to pass it through, and that is also dependent on this phase, because this will go to here, right? And then we'll determine that later next time, because we ran out of time now. Okay, so that's the path. Once we do that, we just evaluate the Gaussian integral and get the final form. Okay, so up to here. Any question up to here before we go? Okay, so that's we'll continue finish up this derivation. All right. Okay, we stop here.
Thank you.
Okay, bye. All right, so let's go back to the asymptotic, which exactly we need that one. Actually, we actually need that one also. Like, for some reason, your textbook changed the two variables, so go back to your textbook variable. So your textbook changed to this is a z, and this depends on t. This is z. This is a z. This is z. This is t. Z minus 1 over z. Okay, so and in that case, No, I'll go a little fast because we already started this way. You remember that we discussed that. We said this is W as a function of Z, the integration variable. T is a parameter in this case, and consider T large T, right? And the idea is we set we basically do a Taylor expansion. WZ is equals to W as Z sub 0. We evaluate Z0. Z0 less than half W Z square. Z0 square equals high order. And this contour starts from 0 to 0 infinity times e to the I pi. So the theta is 0 here. Theta is pi over here. So that's the branch that this contour C sub 1 is defined on. All right, so the settle point method is basically setting dw dt to 0 and to choose what the C sub 0 is. So W dw dt, dw dz is t over 2, 1 minus 1 plus 1 over z square, set it to 0. The z square equals to -1, right? And then so you have two settle point plus or minus I, but we're choosing z0 equals to I, which is on this branch is I, e to the I pi over 2. Basically this one. This is a settle point. And so you last time we talked about we need to determine how we cause this settle point. It's something most likely this one if I remember correctly, but we need to figure that out later because we already talked about we want to go through a settle point along the valley. It's like you want to cross a mountain, you have two mountains, and you want to cross the mountains through the lowest point of valley between the two mountains, right? And that we will need to figure that out, but for now we're just determine the settle point. So there's one, actually there's a minus I here. And we don't go through that, we go through this one. So we choose C sub 0 is this one. And now we can evaluate the this one. And the W C sub 0 is just, this is I minus 1 over I, which is plus I, so 2I, so it's I times T. That's the leading dependency on T of this function, exponential IT, that's the leading order. And later we'll need to evaluate this at the C sub 0 also. But we'll figure that out a little later. And now we need this term. This is the term that after you substitute C0, obviously, this is by choice, this is 0. Okay, and we have this WDC square as just take another derivative, will give you minus T over C Q. And then we evaluate C sub 0 becomes C sub 0 Q, which is C sub 0 as e to the I pi over 2. And then you take the minus 3 factor, minus 3 power, right? So minus T e to the e to the 3 minus 3I over T. Right, and all right, so this is going to here, right? And now comes the how to determine the path. So you can actually follow your textbook. The textbook just look up the formula in section 12, and then just plug in the formula, and after you calculate everything and calculate the phase, and then calculate what the phase of this there's a formula. You have a phase angle. You determine what the phase angle according to the formula, and you can do that, but without the understanding of what we are actually doing. And one problem with that is there's ambiguity. In that formula, there's a choice between two possibilities. Basically, the two possibilities means you want to cause this one way or the opposite way. So there's the angle is ambiguous in this sense, right? So if you don't know what you are doing and you don't know the mechanism of the method, then you get stuck. What sign to use? Basically, it's plus or minus sign problem. And you just plug in the formula, and so therefore, going through this so that you have some understanding, so you know what those two choices are meant to be. So then you know you have a way to determine which value to use or which sign to use. Okay, so the idea is just plug this into here. So remember, this is in the exponential function, right? We want to make it like a Gaussian integration. We want to make it exponential minus something square, right? And then the something is a real number, so we want to get which of the phase, basically, and make it a Gaussian integral along that path, right? And if you substitute this into here, so just consider this term. We want to make this term minus something square, some real variable square, right? So plug that into here. So it's just consider this term, just 1/2 or minus 1/2 minus t over 2, and we consider positive t, and then e to the minus 3i pi over 2, and then you have c minus c sub 0. Now comes this variable. So this is our c sub 0. Whatever along this line is c, right? So c minus c sub 0 is basically relative to this one. So if you have if the path is like what we have, so this is you can actually define the new variable c minus c sub 0 is this whatever c, right? Define that as c, right? And now and then you can write it like c absolute value, the compact absolute value exponential I theta. So this theta, say if you are going along this path, near the saddle point, you're going along this path, so that would be your theta. This would be your theta. Okay, so we want to determine what theta we will use. So in that case, this is let's plug that into here. So c square will be c minus c sub 0 square is c square e to the 2i theta, right? And now you have a minus sign, and then you have this two, combine this two. So let's just combine the exponential function. It's minus t over 2 c square exponential. You have I 2 theta minus 3 pi over 2. Right? And in this case, we already have a negative sign just by our function, the functional form of w. And so we want to make the rest positive and real. So to do that, the choice of theta to make it like that is when this is 0, right? When the whole exponential function is 1. So 2 theta minus 3 3 pi over 2 is 0, or theta equals to 3 pi over 4. So this is continue writing. This equals to minus t over 2 c squared if 4 theta equals to 3 pi over 4. Okay, so now that's what we'll do. So get the minus real number square, a real variable square. Okay, so that's what we started to do. So theta is 3 pi over 4. In this case, I already draw it like this one. So this is pi over 2, 3 pi over 4 is this. So theta is 3 pi over 4. And then we want to go this way. So this is our theta. So the formula will give you either this choice or the negative of this one, or see, either negative 3 pi over 4 or this angle 3 pi over 4 but pi, or 7 pi over 4. So those represent the two signs. So basically, if you choose the other angle, you get a negative sign. Right? So, but this is the phase that we'll use. Theta is 3 pi over 4. Okay, so now we have everything, and so we just need to substitute everything into the integral. And so let's just say that this is all our work. And then so h mu 1 t, or t tends to infinity. This is just the leading order. So basically, you require really large t, because again, we discussed that we are not including this factor in the saddle point. And some people will call this what we call the stationary phase method. It's not including everything. So if you include everything, it's the saddle point method. But we are assuming the saddle point is very narrow, and the narrowness is determined by how large t is. The larger the t, the more narrow this peak or the Gaussian, because t is inside the Gaussian. If t is large, the Gaussian is very highly peaked, right? So so basically, we are considering this limit t goes to infinity. We can assume that the Gaussian is highly peaked, very narrow. So everything else we evaluate at c sub 0. Okay, and okay, so let's just write this one for pi over I, and then this is this becomes c sub 0. Take out from the integration. Integration is just the exponential factor. So a c sub 0, so exponential I pi over 2 and minus nu plus 1. Okay, so this is coming from this one, and using c sub 0, this one. Okay, and the rest is integration, and we'll figure out the limit later. It's very straightforward, but just copy that. This part has versus this term, you are e to the it, right? And the second one is e to the this term. Second one is this term, which is this term. I said this term, right? So minus t over 2 and the c squared. Oh. Right, and now the dtt, so this dz, so this is dz minus c0. It's this one, so dz is d cut c, or and remember cut c is I theta, so this is you can say that you can define a real variable, so or the magnitude, say like this. although we are integrating on both sides. So both sides, when you integrate different sides, you need to change the sign, right? And then e to the I theta. So this theta is coming out from this integral. The e to the theta is 3 pi over 4, right? And then this d, c, right? And obviously this is absolute value, so we actually have two of this way. So when you go up to the top and then go down, both will give you the same contribution. So you can say now determine the limit because it's highly peak, just a little bit along the going through the saddle point. So basically this is a saddle point. If you go along to see, right? This is Gaussian. It's highly peak. So as t goes to infinity, it's very narrow. Although we are actually not integrating, we're just integrating over a very short period, a short distance over the saddle point, but because it's so narrow, so we can say that this is essentially going to infinity. And we're separated into two parts because we have this absolute value definition. Basically, we are saying that this integration will be going from like minus infinity to 0 and then 0 to infinity. And both give you the same contribution because this is an even function. So we can say that this is 0 to infinity and then multiplied by a factor of 2. Right? So that is everything except that this integral. Now come to the memorization. Do you remember what the Gaussian integral value? Let's copy everything first to pi I. Exponential minus I pi over 2 nu plus 1 exponential it and then plus I 3 pi over 4. Right, we got everything except the Gaussian integral. The Gaussian integral, so what is that? So exponential function minus a x squared dx. You can say 0 to infinity or minus infinity to infinity, doesn't matter. What is that? Square root of pi over, it must be a square root of a because you want to, so if you combine the square root of a here, and you need to divide it by square root of a, right? And that becomes a total square, and that one will give you square root of pi over 2, right? Square root of pi over. Let's see if we get it correctly compared with the textbook square root of pi over 2a. Right? Oh no, square root of pi. Square root of pi over 2. Yeah, the 2 is outside. Right? Square root of pi over 2 square root of a. Right? That's more like it, right? So basically it's you have square root of pi, and you have factor of 2, and square of a is square root of t over 2. And see if this is correct. So it's a little bit low. Let's cancel the 2. You have minus I. I mean, that doesn't really matter how you write it. And the square of pi here, and square of t here, right? You have square of pi, square of t, and exponential function. Everything is inside the exponential function. You have it, and then this factor. You have minus I. That's the second term, minus I pi over 2, and then plus 3 pi over 4. So altogether is just pi over 4, right? And then minus I pi nu over 2 plus I pi over 4. If I got it correct, I think. Let me look at it. What the textbook got? What the textbook got? Oh yeah, I'm missing this. There's a square root of 2 here. In the denominator is a square root of 2. The textbook got square root of 2 pi I. You have this I in here. You have this I. That's kind of ambiguity because this I is defined in the Hankel function. So that one doesn't have a phase. So this is I in the denominator. So you can say it's minus. If you get rid of this, it comes minus pi over I pi over 2. If you choose I equals choosing this is minus e to the minus I pi over 2. So this combined with that, change the sign to minus pi over 2. We get right, minus nu pi over 2 minus pi over 4 it square root of t square root of pi square root of t. Yeah. Finally, we got the same as your textbook, the plug in the formula, right? The crucial thing is this one that I always not memorizing. Okay, that will give you the correct numerical coefficient, which is important, right? But the leading order is this one, and the phase is also can be important. This phase, the most important phase can be is multiplied by the order nu. There's a phase factor depends on nu, and then this is the extra phase factor, which sometimes is not that important. The whole thing shifts a little bit. And there's a square of t in the dependence and in the coefficient, so everything will decay slowly in the manner of square of t in the denominator. Okay, so that's actually how about the time? 5 minutes left. Okay, at least we got it done. This is the most important thing because once we have that, H nu 2 is just the complex conjugate of this one. So basically just change all this I to minus I. You get the H nu 2, which is basically the next equation. So now we finish 14.125 and 126. Okay, and then the rest will be straightforward because just by the definition of all other function, like we have like the J and Y related to the Hankel function. Let's use this 5 minutes to figure all these things out. Right, because we start out the definition of the Hankel function defined in 14.7677, H nu 1 is J nu plus IY nu. H nu 2 basically is the complex conjugate for real argument. Right? So that's the 2. So for J sub nu, it's basically add the 2 of the divided by 2, so 1/2 of H nu 1 plus H nu 2. And H nu 2 is the complex conjugate of this one, right? So basically you get 2 of the real part, right? 2 of the real part of H nu 1. So basically, this is the real part of this one. So it's t goes to infinity. Now everything depends on t instead of z because the text will change. the choice of your variable. So this is the two of the, not just the real part because we divided by 2. So the square of 2 pi t. The real part is just the cosine, assuming everything is real. I mean, except the I, everything is real. Cosine t minus pi d over 2 minus pi over 4. Okay, so that's the leading of the asymptotic expression for Bessel function. Okay, okay, so that's straightforward. And now y is just h nu 1 minus h nu 2 and divided by 2i. And minus of that will give you 2 of the imaginary part of this one. I mean, 2i of the imaginary part, right? Because your I imaginary part, 2i of the imaginary part, and I cancel with I. The 2 of the imaginary part divided by 2 is just the imaginary part of this one. So tends to the imaginary part is basically the sine instead of cosine. Right, and see if your textbook has those written up. I mean, because the textbook has a second method, so probably write those a little later. Later in the section. So basically that you compare with equation 14.140 and 141. So now your text will change back to Z. It's just string, but that doesn't matter. So the dependence is the same. In those equations, there's a P and Q coming from the more exact method. So P and Q will be some kind of polynomial in Z of inverse Z. But for leading order, it's just set P equals to 1, Q equals 0. So that will give you the leading order will be cosine nu pi over 2 minus pi over 4. Yeah, that's one. That's the one. And then the y is the same thing with sine, changing cosine and sine. Okay, so this method, this saddle point method of stationary phase method, give you the leading order. But to get the high order, you either need to keep doing the higher order in saddle point method, or using this the second method in this section, which we'll skip. That's a really long discussion. We'll skip that. And I think it's out of time. I mean, the rest is the dependence on K, the modified Bessel function, I and K, which need a little bit more discussion, but not a whole lot. But we'll finish that up on Friday. And let's finish up the asymptotic expansion in section 6. We just have a couple things. I mean, I skipped the second part of the section, the second method. But, so for us, we first got the expansion for H, right? H1. And this is essentially 14.125. But we just change back to this Z dependence is instead of T, because later on the second part, using a second method, for some reason going back to Z. So to compare that, because we want to get to the same same form, especially for the modified Bessel function. So that is you see, it's the infinity for positive Z. Positive and real Z, obviously. This is two. E to the I, and that's Z. Going back to Z. Z minus mu pi over 2 and minus pi over 4. Okay, so the first thing we did using the saddle point method, we got that, and then with the other one, H2 is obviously just the complex conjugate for real Z and real nu. Wait, so that's simple enough. And then J nu, we last time we already showed that it's the real part of this the H function. So it's basically cosine, same thing. And then the y nu is this, the sine part, right? The imaginary part. Right? And these are just the leading order. I mean, the second method will give you a series of inverse power of Z. Okay, and now the modified one, we need to go back to the definition. So the last section. So there's I and K, and looks like K will be easier because K is directly defined by the H function. Let's see, it's defined in 14.6. Now this is using X. The argument that the variable for argument is just all over the place. But that doesn't matter. Change it back. 2 I nu plus 1 H nu 1. Now this is imaginary argument for real Z. Right. So that is that. Right. And first of all, of course, you need to accept the argument that you can take this form which we derive using a real and positive Z. We derive that using the saddle point method because that is required. And then we just accept that we could, after you get that, you can use analytic continuation to extend the application to imaginary or compact Z. Right? And which we are not showing that, but we just accept that that should be the case. Now, all you need to do, if you accept that, you just substitute IZ into Z. So all the Z change to IZ for this one. Over 2. You have some kind of ambiguity of the I, because all these phases are in exponential function. You need to choose a branch for I, because you have this potentially fractional power. But anyway, I think let's try the e to the I pi over 2 as I, right? And then you have u plus 1. Let's change that to that. And then H has this all this vector. So I should actually put this vector infinite u over I. And there's actually another I. So we're not totally done with the phase. extra I here. Right. Well, and then all this. This is just for the H1 is plus sign, so plus. So you can say include everything in the I. The plus Z becomes IZ, right? And then minus mu pi over 2 and minus pi over 4. Okay. So that actually needed to work out the coefficient. You have pi over 2 divided by pi over square root pi over 2 square root of 2 pi over 2. And then the leading order is I times I is e to the minus z, right? This is negative. And now the new pi over 2 part cancel. Right? And that is good. We'll cancel this one with this one. Say that again. Oh, yeah, you're right. Yeah. It's IZ, yeah. It's a 2Z. All right, so, and now the rest is, you have I, you have pi over 2 minus pi over 4 becomes a pi over 4. But then you have this I in the denominator. I is, again, we choose e to the I pi over 2, and then in the denominator is minus 1/2. So as I pi over 2 minus 1/2 is minus pi over 4, right? But this one, you see that? Yeah, I again, so I minus 1/2 power equals to e to the I pi over 2 minus 1/2, right? And then equals to e to the minus I pi over 4. So that go into here, and then these two cancel. All right, so turns out cancel all the phase, which is needed because K, the I and K are defined as real function. Finally, you define it as real function. So suppose that you should get rid of all the phase, becomes a real function, a real argument of this for real Z. So that should be the asymptotic, the leading order of the asymptotic expansion for K. And let's now go back to, the second method actually use another integral representation of K nu, starting with equation 14.128. And except that we are not going through that because it's very long. First of all, you need to show that this is a correct integral representation, which means it satisfies the modified Bessel function, and also it has the same form as what we defined before. So you need to check a limit, like the small z limit, and it gave you the same form in that limit. And so you identify that as the same K, and then you do an expansion of the inverse power of Z and get the, in this case, you get the power series. Actually, it's an infinite series for most situations. Sometimes it's truncated and get a polynomial, but you get an infinite series, and then you get this P and Q function of inverse of Z power of Z, and that those are the infinite series. And so you can get more exact than the Satterthwaite method using this integral representation, but it's a really long discussion, so I don't have the time. We don't have the time now. But just look at the final form and equation, just to compare with equation 14.134. hopefully we got it correct. So yeah, square root of pi over 2z exponential minus z. And in that in this equation you have this p and q, but the leading order is that p is 1 and q is 0. So, or I mean it's leading as 1 over the argument. So that in leading order you can treat it as 0. Right, and so we got it correct. Let's just so kind of not like a justification. You can say that this is originally from the H function defined for mu z, but we treat it like imaginary argument. But finally, you get to this form, which is the same as a more exact method. And in this case, it starts with an integral representation for mu z. This mu z. So both methods agree, at least to the leading order. So that another justification that the analytic continuation should be valid. Okay, so that's K. All right. So and then with really nice form, so you actually don't have, you can forget about all these phases for the K function, and the I will be similar, but it's not. Just you need to pay attention that the leading coefficient is different from K nu and I nu. So we need to work out that a little bit. So for I nu, we use the definition. At first, we can use what we define, how we define. So I nu is defined, yeah, in equation 14.99. So I nu x comes z now, defined as I with the minus nu power j nu imaginary argument. Okay, and now again we substitute what we have here is j. Again, that tends to, you have square root of, you have this I. Now we'll work that out first. So e to the I pi over 2 divided by minus nu, so minus I pi over 2 nu for this one. And then j nu, this one is square root of pi at 2 over pi. Now again you have a I in here, I and z. Right. And then cosine of instead of using cosine, we'll go back to the Euler relation because we're using complex argument. It's best to use for sine and cosine. The exponential function is just sine and cosine. So this is cosine is one half of exponential function I, and then so basically it's the same thing here, right? I, right? Or just write out I z becomes I z minus 0.2 square root 4. So, and plus the complex conjugate. And plus e to the minus I. I should say plus the complex conjugate, but still the z changed to minus, c changed to IC. So take the complex conjugate of the original e to the this I times this I, and then takes the complex conjugate, and then take the substitution. This one helps. The bracket is not quite right. Okay. So all we want to get is actually get back to the correct phase, and one argument you can use immediately is that for positive z, the I times I is negative. So this is exponentially small, right? And this one is exponentially large. So you can ignore this term, compare with this term, right? Because we are talking about asymptotic limit anyway. So now this is, now we need to get everything correct. So this 1/2 in here go into the square root of 2 pi z. And we need to keep track of all the phase, right? You have at first you have this I times I is -1, so it's e to the z, and then everything else phase. So you have plus I, right? This is minus. So these are all these two terms are plus. U pi over u minus pi over 4. And then this term is minus u pi over 2. And then this is again the same thing, right? And e to the, this I to the -1 is minus. This is plus, yeah, this is plus. Sorry, this is plus. And this is minus pi over 4. Okay, so everything cancels. It's canceled that. But there's no imaginary part in here. So that's this part is the correct exponential asymptotic form. So you compare this with k. Compare this with k, right? So it's exponentially large instead of exponentially small, and the form has this that's the different dependency, different form in the coefficient. Let's see if I got it correct. So hopefully, so let's look at another way to do it is this. What is the I in the second method? Yeah, 14.143. So e to the z divided by 2 pi z, and then p as 1, q as 0. Okay, so that is the correct form. So again, pay attention that these two are not the same. The coefficients are not the same. One is exponentially small, the other exponentially large. The coefficients are not the same, so you don't get confused about it. Okay, so that's the order, leading order, and then again this if you need the higher order term, you go back to this p and q function, and should use in enough term for your application. One thing to be careful using asymptotic series is that those are divergent series. So to use that, you need to be a little careful. So basically, you keep summing the different term, and the term will initially get smaller and smaller, and somewhere along the line will get larger, go back to larger. So you need to stop summing. After you get to the smallest term, you just truncate your calculation. Just use that as your approximation. If you keep summing it, it will eventually go to divergence. Okay, so that you need to be a little careful. Right? Those are, I mean, numerical method. Anyway, if we don't do that, we are done. But maybe there's a little discussion based on that series, that the accuracy of how many terms you need to get an accurate asymptotic approximation. And the bottom line is because there's a phase in here, there's the order in the phase. High order Bessel function will be less accurate. If you just the leading order will be less accurate. because it's more difficult to get the phase correct than the magnitude. So for higher number, mu is larger, then you need more terms. So basically, that's the basic idea. Okay, so I guess you're done here. Any question up here? So, the leading order is most of the time you just need the leading order as in many situations, especially analytic work. So you just take the limit of really extremely large or the limit of infinite argument. Then you just use the leading order term. Okay.